So I'm going to try to explain the parts that were confusing to me about the OpenGL Graphics Pipeline. I might take some pauses in between to think about what I have to say because there's a lot of things to explain, and I'm doing this live. So pretty much the graphics pipeline is this. So we're gonna send some vertex data to the vertex shader, which is a program that you have to create. Then you pass that, the OpenGL passes that data to the geometry shader and then the shape assembly. Then it does the rasterization algorithm, which just calculates the pixels that are going to be drawn based on the points that you're sending. Then it sends that to the fragment shader, which colors the pixels, and then does some tests to see the depth and the lightening or the texture of everything. So I'm going to focus more on the vertex shader and just the parts that were confusing to me to explain, to understand. So yeah, so pretty much the way that it works is that you're going to pass an array of floats to the vertex shader as a data. And the way that you do that is by using buffers. Buffers are just a space in memory that's a good way to think about it is like a bridge between your code and OpenGL. So you're gonna call a bunch of OpenGL functions that are gonna specify how the array of floats that you're sending is gonna become data inside of the shader. So one of the things that were confusing to me is that when you code the shader, each variable that you put inside of the code is gonna have a location, and then you're gonna have to specify to OpenGL what the location is in order for OpenGL to understand what the data you're sending to OpenGL is related to. So for example, in this example here, you have location 0 and location 1. And then one of the functions you call to set up the buffer is this one, vertex attribute pointer. So here, the first argument is going to specify the location of the variable you're sending data to. So this is 0, so that means that the data you send to this buffer is going to be related to this variable here because the location is 0. So that's one of the things that were kind of confusing. And the way you pass that data is by using these objects here, which is vertex buffer object, vertex array object, and element buffer object, which is just different variations of how to structure the data based on OpenGL. And I'm not going to talk too much about that because still not very clear. But pretty much these pictures here show. So you specify the data you want to send, and how much of the data is going to be for each part that you're going to send. So the shader just draws one point at a time. So it's like you're slicing the array of floats that you're sending, and then you're telling OpenGL how the structure of the floats has to be used so that the shader makes sense of the data you're sending. So the stride is just pretty much how much you have to go from the first place you're sending to the next one to get the next value that you're sending. So it's like you're saying to OpenGL that you're going to send 3 floats, and then they're going to start at the index 0 of the array. And yeah, the next one is going to be 12 steps ahead because a float is 4 bytes. So 3 times 4 is 12. And then, yeah, pretty much that's it. So that's how you tell OpenGL how to get the data you send. And then basically your responsibility is to translate that data you send in the vertex shader code into normalized device coordinates, which are coordinates that go from -1 to 1, and there are 2D coordinates. And then OpenGL is going to take the normalized device coordinates and is going to translate that into screen coordinates. And it does that by this transformation here, just calculates like this, based on whatever you set on the GL viewport function. But the part that was confusing to me is how exactly do you do that? So like one thing to understand is that you're going to have multiple different coordinate systems you're going to use. So the calculation that is done is this one. to translate from the data you send to the normalized device coordinates. You multiply by 3 matrices. One is the projection, the other one is the view, the other one is the model, and the other one's going to be the position of the data you're sending, which is the variable here, through the buffer that I just explained, these buffers here. So you can look it up later. I'm not going to explain more about this. But the coordinates work like this. So you have 2 different coordinates, which one is the local coordinates of the point you're sending, and the other one is the world coordinates. But in the beginning, these 2 coordinates are going to be the same, because what you do to transform from the local coordinates to the world coordinates is by multiplying the points by a matrix called the model matrix. And after you do that multiplication, then it's like you're translating the local coordinate into the world coordinates. And the reason you do that is because the best way to perform rotation, translation, and these transformations on a point is by multiplying a matrix by another matrix that is going to be either translation, rotation, or scaling. So in order to do that, you have to multiply the 2 matrices by each other. So the model matrix is going to hold the information of where the point is on the local coordinates. And then you're going to multiply the matrix by another matrix that is going to perform the operations that are necessary to translate the point or to move the point around. So if the local coordinates were the same as the world coordinates, what would happen is that after you multiply by the translation matrix, for example, let's say you move this one to the right, what will happen is that everything on the road would move to the right as well. So in order to separate different objects in the visualization, you have to separate them into different coordinates. So you're able to move the points around into their own coordinate space. But the thing that is confusing to understand is that both the world coordinates and the local coordinates, so this one is the local, this one would be the world, they are both supposed to be normalized device coordinates, which go from -1 to 1. And in the beginning, the way that you are going to set up the model matrix is going to depend on the way you want to send the data to the vertex shader. Because if you're sending the data in values that are outside -1 and 1, then obviously they're not going to show on the world coordinates, because the world coordinates are from -1 to 1. So you either send the data in normalized device coordinates, which are these values here, or you send them in whatever coordinates you want, but then you have to do additional calculations in them to transform those coordinates into normalized device coordinates before you send them to the shader. And then it's your responsibility as a programmer to do the calculation here, which is going to translate the position of the local coordinates into the world coordinates by multiplying by the view, which is the camera matrix, which is just another local coordinate system. You can think about it, the camera as being the same as an object. So when you're multiplying by the view, what you're doing is just shifting the final visualization to be in the coordinate position that represents where the camera is supposed to be on space. So it's like you're viewing the space through the local coordinates of the camera. And once you multiply by this. And the projection matrix is the matrix that is going to give the illusion of 3D by doing a bunch of calculations that you're going to encode inside of the matrix. Which I'm just going to briefly explain, I'm not going to dive too deep into the explanation, but yeah. So just to reiterate, you're going to send, usually, I think, you send in normalized device coordinates already, so we don't have to normalize. But however, 3JS, they send on a different scale, the coordinates, and then they perform the normalization. And a good way to think about normalization is just like as if you are shrinking the whole coordinate system so that they fit the -1 to 1. So like you keep the relative position that the point would have if all the scales were converted to that range that you want to convert. That's called normalization. So you do the normalization, you pass the coordinates on whatever arbitrary number you want, then you do the normalization, then they're going to be between -1 and 1. So hopefully that's clear. So you send the data in this value, and then in the beginning, usually, if you don't do any translations, the model matrix is going to be the identity matrix, because the identity matrix doesn't change any of the values once you multiply by it. So it's just going to be the original values. So the model matrix is not going to do anything in the beginning. You're just going to multiply the values and they are going to be the same. And then you're going to multiply those values by the camera matrix, which also is going to be the identity matrix if you don't change the values of the camera. And then you're going to multiply that by the projection. And then the final coordinates that the GL position is going to have are going to be in normalized device coordinates. And these, so pretty much the way to think about it is that as if these two references, these two coordinate systems are overlapping here. So the local is overlapping with the road. And the road coordinates are just the coordinates that OpenGL uses at the end. But yeah, so they're pretty much overlapped if you don't do any translations, because the values, and you normalize the values of the data that you send, because then they're going to be the same values. The only reason why they're separate coordinate systems is that once you want to do the transformations on the local coordinate, it doesn't change all the values on the world coordinate, and then it doesn't mess up the other objects. You can separate the objects that you want to change. The other thing that is very confusing is that all these matrices are 4x4 matrices, because what happens when you multiply one matrix by the other is that the only way to perform the translation between matrices is going to be if you have a 4x4 matrix, because the translation operations are going to be stored on the last row here. So this is the matrix that they use. And this is just called a homogeneous matrix. So this W value here is usually going to be 1. And yeah, it's pretty much 4x4 because you have to store the translations here. And all the operations don't change the value of W except the final one, which is the projection transformation. And the projection is just doing some calculations based on the triangle, which is going to be a consequence of this field of view here, the frustum. And then based on the angle of the frustum, it encodes the calculations inside of the matrix that translate that give the illusion of depth by dividing the x, y, and coordinates by z. And yeah, I'm not going to explain too much into this, but so here is the pipeline from the data to the GL position. So what's important to understand is the W. That's the projection matrix is going to change the value of the W, and every time you change the value of the W, you have to divide all the other values by that value so that the W is 1 again. So the final GL position here is going to have 4 values actually, because of this 4x4 matrix and this value of W. So you can see here this vector 4, and all the matrices are 4. So GL position is going to be 4. So it's going to have the final W value, which is going to be changed based on the projection that you are responsible for passing the projection matrix. And the projection matrix is going to look like this. It's going to have, actually, let me go to, it's going to look like this. So these values here pretty much, I think these ones, I don't remember very well, but yes, probably this one and this one are used to normalize the value of the coordinates so that they are between 0 and 1, or between -1 and 1, so that they are normalized. And then this -1 here is used to set the value of W to -z. I don't remember really well why this happens, but I think that the reason why it happens is because you have to do these other calculations here on the projection matrix in order to create the sense of projection. So it ends up affecting the value of W. But the important thing to understand is that after you calculate the GL position, so you're going to pass point by point the data according to the specification you give to the buffer. You're going to pass point by point here to the shader. And then you're going to create the matrices that hold the relative position of the model, which is the data you're sending, that is going to create the object. And by the way, all these values here are in relationship to each other. So it's like the coordinates that I showed here. So like when you're modeling, when you're creating an object, it doesn't matter the coordinate systems of the world, because all that matters to create the object is the coordinates that they have, the points have in relationship to themselves, because that's what's going to create the geometry of the thing that you're doing. And then the model matrix is just going to move all the points responsible for creating that geometry and in the world space, because they're going to shift in local space, and that's going to be translated into the world space because they're overlapped. So hopefully that's understandable. So you can imagine that you're sending one point here, and that point is the position, and that position has the 1 here, which is the value of the W. Then if you haven't done any translation or anything else, this is just going to be the identity matrix, which is just going to preserve the position. So it's kind of like you're overlapping the local model space with the world space that goes from -1 to 1. And then you're going to multiply by the view, which is another matrix for before that represents the positions of the camera, which is pretty much the same matrix as the model, like it's the same structure, but obviously they hold the different information. One holds the position of the object that you're trying to render, the other one holds the position of the camera. And you multiply by the camera so that the final visualization is from the perspective of the camera. And then the projection matrix encodes this information that once you multiply the other matrices by this one, it's just gonna, based on some triangle math that you can read here, it's just gonna create the illusion of 3D, and the final coordinates are gonna be this homogeneous coordinates, which is gonna be a vector of 4 values. And then what OpenGL is gonna do behind the scenes is gonna divide the x and y, z values based on the value of W. That is going to be different at the end because of the multiplication by the projection. If it's not different, then it doesn't matter because it's just division by 1. And before it does that, it's just going to check to see which values are inside of the -1 to 1, which is called the clip space. And the values that are outside are removed, because if they're not, then you have division by 0, which obviously breaks everything. So you have to check first if they are inside of the space, and then if they are, you divide everything by W, which is called perspective division. So I think that's the things that were confusing to me. I think I explained everything. So after it does that, the final thing that it does is just convert the normalized device coordinates. OpenGL does. It should convert the normalized device coordinates into screen space. But it does that after it does the rasterization, I think, and the fragment shader runs. So as a programmer, you're responsible for creating the camera and the projection matrix and multiplying them inside of the shader. And you were responsible to normalizing the positions of the data that you send so that the values are in the range between -1 and 1. And OpenGL is responsible for taking this, which is going to have the 4 values, and then checking to see if they are inside of -1 and 1 range in the clip space. Then it's going to remove everything that is not, and then it's going to divide everything by W, which is the final modified value that the projection matrix changes. Then once it does that, it has the final visualization, which is in 2D space, because the multiplication by the projection transforms everything into 2D coordinates. And then the way that it does that is just by dividing the x, y values by the z value. And that creates, based on the angle of the projection, creates the illusion of distance. So after it divides everything by W, it has the final position of the point, and then it's going to translate that based on this formula to get the actual position on the screen of the pixels, and then you're just going to color everything and render whatever happened. So I think that's pretty much it. I don't remember if there's something else that I missed. There's a lot to talk about, so. So this is pretty much the final matrix. I think I'm gonna read this here and then I'll stop. The values that matter are these ones on the projection matrix. So this value is used to remap z to 0 to 1. This one is used to remap z to 0 to 1. So the 2 by 2, 3 by 2. And so this one and this one are used to remap from 0 to 1. Then this sets the W to -z. So the -1 value there, this value, sets W to -z, which OpenGL is gonna divide everything by. And So the output of the vertex shader requires the coordinates to be in clip space. OpenGL then performs perspective division divided by W, value of homogeneous coordinates, or the clip space coordinates to transform them to normalized device coordinates. OpenGL then uses the parameters from GL viewport to map the normalized device coordinates to screen coordinates, where each coordinate corresponds to a point on your screen. Viewport transform. The data sent to the buffers in order to draw the shader has to be in normalized device coordinates. If it isn't, just multiplying them through model, view, and projection matrices won't automatically convert them. So they will be outside of the clip space in that case, because the scale is off. The GL frag coordinate variable, this is a variable inside of the fragment shader. So both the vertex and fragment shader are just code that you create, and then you use a bunch of OpenGL functions to create the actual program that is going to create the object that is responsible for managing this information that receives through the buffer and sends to the GPU to draw everything. And then you link them, and that's called the program. And then you call the functions that are going to determine how the data is going to be rendered in the end. So how is the array here is going to be consumed by the buffers based on the way that you set it up here, based on the location of the variables, what variables you're passing, the strides, which is the distance between each time that the variables are located into the array here. That's going to go into the shaders, shader code. Then you are responsible for making sure that that falls into clip space so you can see. And another thing that is important to understand is that moving the camera doesn't move the world coordinates. The world coordinates are always the same. So they are always the same, which is determined by OpenGL, which is the clip space, the -1 to 1. They are always going to be the same. What's happening when you change the visualization is you're just moving the coordinates from the camera. And then because you're multiplying everything by that matrix, the final stuff that is going to be shown on the screen is the visualization being parsed by whatever the camera position is at. And based on the projection matrix, it's just going to create the illusion of 3D. So it's not like you're moving the road around, you're moving the camera around, the road is always the same, and then each object is going to be calculated based on its relative position, which is going to be used based on the data that the shader receives, and that the way that you set up the buffers so that the data is received by the shaders and creates the different points on the visualization. Oh, just remember the final thing that happens is that it has another buffer called Z buffer. OpenGL has Z buffer. And then what the Z buffer does is just calculates, it tracks the positions, the Z positions of each thing in order to see what thing is in front of the other thing. Because obviously if something is behind something else, then it's not supposed to be rendered. And the thing that determines which pixels are going to be rendered is just the rasterization algorithm. It just takes the points that you draw with the shader, and then it's just going to calculate which pixels are supposed to be drawn based on the distances of the points. And the way that it does that is by finding the barycentric point, which is just a good way to think about it, is just the middle of the triangle. So there's interpolation to see where the middle of the triangle it is. Interpolation is just a fancy way to say the middle, I think. So the middle of the 2 points, the sides of the triangle, based on that, it finds the middle of the triangle. And then it runs an algorithm that is going to determine inside of the triangle what pixels are going to be drawn. And then after the final step, after it does that, and after it runs the fragment shader, then it does this depth test to see which one is in front of the other. And also there's a stencil test to see what colors are going to be shown, which I don't remember very well. So 4x4 matrices are used in CG, computer graphics, to transform points and vectors. They encode rotation, scale, and translation. Yeah. So the reason we have 4x4 matrix, the homogeneous coordinates, is so that it can encode the information of the translations or the movements inside of the matrix. The way you do the transformation is just by multiplying the matrices that hold the information for each thing based on the other matrix, which is going to perform translation, rotation, or whatever else. And translation, for example, is like X, Y, Z, the amount you want to move in the right, the final column. And then 1 by 1 in the diagonal, and then you just multiply by that by the other matrix, and then the final value of the translation rotation is going to be at the end of the last row of the matrix you're translating. So a good way to think about the matrices is just that it's like a placeholder to handle the state of each thing on the visualization. So it just captures the state of each thing. Except the projection matrix, which does the transformation of the visualization. So that is 3D. Points are transformed from clear space to clip space in the vertex shader. The input vertex is converted from Cartesian coordinates to homogeneous coordinates, and its W coordinate is set to 1. The predefined GL position variable in which the transform point is stored is also a point with homogeneous coordinates. So when the input vertex is multiplied by the projection matrix, the normalized step is not yet performed. GL position is in homogeneous clip space. So GL position is going to be a vector of 4 values. When all vertices have been processed by the vertex shader, triangles whose vertices are now in clip space are clipped. Once clipping is done, all vertices are normalized. The x, y, and z coordinates of each vertex are divided by their respective w coordinates. This is where and when the perspective divide occurs. So I think that's pretty much it. I think I remember everything. So if you want to understand more, just read these articles here from Scratch Pixel from the beginning. They are the articles that explain this stuff. And also these articles from OpenGL here. These articles, this one is going to explain how to manage the buffers from OpenGL, the hello triangle. So yeah, I think that's pretty much it. So I'm going to stop here. If I forgot something, I'm probably going to do another stream trying to explain. But